do you know the probability of combined events? It's okay if you don't, because Owen will explain it to you.
Let's start with definition. When two experiments are conducted together and the results are considered as combined events. So for example, there are two different experiments. Experiment number 1, tossing a coin. Experiment number 2, roll a dice. These two are different events and have different outcomes. The outcome of tossing a coin is head and tail, and all possible outcome for rolling a dice is number 1 to 6. The possible outcome for combined events as the above is 1 head, 2 head, 3 head, 4 head, 5 head, 6 head, 1 tail, 2 tail, 3 tail, 4 tail, 5 tail, and 6 tail. There are totally 12 possible outcomes. So here's the thing that I want to emphasize, which is really important, is the lattice diagram. So basically, lattice diagram is not the same chart as the independent events diagram, but it's still like a column and represents the combination of all possible outcomes. So as you can see the formula shown above, the calculation of combined events use the same formula as you have already known beforehand. Numbers of way an outcome can be happen over total number of possible outcomes. Okay, as you already know the conception and every principle is about it, so here's the question that I want to ask for a practice, is that to calculate the probability of getting all heads plus any dices of an even number. So when we face this problem, first of all, you should clear about what's all the possible outcomes and what are the required outcomes. So there are 12 possible outcomes total, and there are 3 required outcomes as shown above because you have to satisfy all the conditions. So as the formula shown above, as you can see, numbers of ways an outcome can happen over all possible outcomes. So you can easily calculate out as the probability is 25%. So basically what it means is that they have more constraints because they're combined events. The constraints are also combined. So let's move to the second part, intersection and union. So let's start with intersection. So there are two sets randomly picked, M and N, and if you see closer, there are actually two elements that simultaneously appear in the two sets 7 and 12. And these sets and these elements share the same sets, or the sets share the same element, and the set of these shared elements, combined elements, are called intersection. So as I'm going to emphasize the intersection, I draw two circles, first of all fall apart, but when they stick together to some extent, the extent that they share are the intersection. Okay, so let's go to the union part. I also give out two randomly picked sets, M and N, and then what the definition of union actually means, the elements either appear in set M or set N. So which means all elements, remember, all elements in both sets are considered as union of the sets. So the denotation shouldn't be repetition as I shown above. So you must be concise and simplify the sets. And then as you can see the intersection as I showed above. So the union are just two circles, the area of two circles, plus the intersection. So the question up here, how are union and intersection implemented in theory of probability? So I give out a specific case 1, and there are a general set and a subset A and B. So the general, you can think of general set as all possible outcome, and the subset A, B are just the way they can appear or the possibility that they can appear. So I have already calculated the probability of getting A, B, union of A and B, and intersection of A and B. And then through calculation, I turns out formula and a little bit of transformation of the formula. So a more difficult case appear, case 2, and I have already shown the formula above. And right now if you deem a general set as X, and subset A and B, X1, X2, intersection of A and B, X3, and the union A and B, X4. So the probability is just everything over X. So regardless of the donation P, so we just talk about A and B itself. So in a circle, as you can see, A and B, and they are the darkened part of the intersection as denoted X3, and then they are X4. So if we can see that X4 is one layer of two circles plus the intersection, and then we have another intersection, so we must minus one intersection because they have already been repeated. So the probability of getting union A and B is A plus B minus intersection A and B, just to avoid a repetition. And also we have to think about if two elements are mutually exclusive, so that the intersection is 0 is a null set, so it still don't affect the way how the formula works, because union of A and B is just A and B, because we regardless the intersection because it's 0. And then another case is that when the two events are independent from one another, so there's a table, and before that we should know that we should be assured of the degree of independence. So if we see as 1 degree of independence, if the total number are settled down, then the probability of getting the BC is not the same probability as getting AD, and the probability of getting AB will not affect the probability of getting either of BC or AD. So you must be certain that the total number are sure. They are uncontrollable variables. So that in this case, we already know how to calculate EI. So the same method, so the probability of intersection A and B is just PA times PB. So in order to represent this, I use two rectangles, but to make sure that the length of it no more than 1 and no less than 0, so that when decimals are times together, they tend to be smaller. So they can now represent it as the shaded area of two rectangles when they meet together. This is the intersection of two independent events. So the formula still works because the intersection is non-zero, and the sum of PA plus PB is still bigger than the intersection.
Question 4. Define Venn diagram. Venn diagram is a set of diagrams that is shown in diagrammatic form to represent a set of data.
Okay, so here's an example of a Venn diagram I'm going to introduce to you all. So there are three sets. Set A, which is 1, 2, 5. Set B, which is 1 and 6. And set C, which is 4 and 7. So now we're going to represent this sets of data using Venn diagrams. Okay, so these three are the visualized representation of these three sets, A, B, and C. But now we can see that they're both A and B have the number 1 in their set. So we can use the intersection, which Owen has talked about, to integral the data, the two sets of data. So we can have this. To represent the whole three sets of data, because the data C, which is 4 and 7, it has no intersections with set A and set B. However, so now we can see so these two are not intersect. Okay. As the definition mentions, Venn diagram is an illustration, a model for us to better understand difficult math questions by visualizing the real data and object rather than picturing in mind. So it is a way for us to better understand the difficult math questions. And before we move to the next part, we're going to introduce the concept about the universal set. So in set theory, the universal set is a set that contains all objects, including itself. So we're going to use this giant rectangle to represent the universal set. So using the example about set A, B, and C, they should be all within the universal set, regardless their numbers and digits and whatever. So it should be represented like this. We're going to use fit it in the concept of the universal set. Cool.
Okay, so here is a practical example of how a Venn diagram can illustrate a situation. Let the universe be the set of all computers in the world. Let X represent the set of all notebook computers in the world. Let Y represent the set of all computers in the world that are connected to the internet. Let Z represent the set of all computers in the world that have antivirus software installed. If you have a notebook computer and surf the internet, but you are not worried about the virus, your computer is probably represented by a point in the blue region. If you get concerned about computer virus and install an antivirus program, your point representing your computer will move into the black area.
Now, since we know that this giant rectangular is the universe, which means that all computers, and X means all notebooks, and Y means all notebooks with internet connection, and Z with all notebooks with antivirus. And also, the condition is you first have a notebook which serves the internet, and the second, you also have a notebook that has an antivirus installed. So let's mark like where the range of U1 can be. So the set is the notebook that can serve the internet. So which means all Y is the range of U1. It can be anywhere your computer, among the whole set of the notebooks that with the internet. And for U2, the notebook which has the antivirus installed, and this is pretty simple as well. It is in the range of Z, which is the notebook with antivirus. So in this way, this kind of set and notation can be easily represented using the Venn diagram. And that is how Venn diagram can be used in simple math questions and daily life. Thank you.